Hello, this is a interesting geometry problem from ISI Entrance. It says that AB is any chord of a circle C, and we want to find out a point P on the circumference of the circle such that PA times PB is the maximum, and point C on the circumference which maximizes PA plus PB. So there are two things that we want to maximize. Um, this type of problem can be handled using differentiation or some tools from calculus where you create, so here is a method that you may use, uh, create a function that represents PA times PB and then differentiate it to find the relative maximum of or relative minimum of it. This is one way by using calculus. We will not use this way, of course. We will be using pure geometry and maybe a little bit help from trigonometry to solve this problem. So let's first look at the first part where we want to find a point P on the circumference such that the product of PA and PB is maximum. First, notice that it doesn't matter where we put the point P. This angle here is always same. So let's call this angle theta. It doesn't matter where we put the point P. So let's say P prime. This angle is always theta because of the angle subtended by the chord theorem. And if I do it on the opposite side, let's call it P double prime, then this is 180 degree minus theta. So what is the area of triangle APB? This is the first hint. You may pause the video here and think a little bit about it. What is the area of triangle APB? Well, what we can say is triangle APB is half times PA times PB times sine of the angle in between. So it's sine of theta if we are looking at this triangle, and it is sine of 180 minus theta if we are looking at the triangle on the opposite side. So it's either this or PA times PB times sine of 180 degree minus theta, but that is sine theta again. So we really can use only one formula. Doesn't matter where the point P is, which arc the point P is, the minor or the major, it's always sine theta. Okay, so clearly if we take the area as half PA times PB times sine of theta, notice that sine of theta is fixed. Why? Because once you fix the chord AB, the angle subtended by the chord at the circumference is fixed. So this sine of theta does not change. The only thing that changes is the product of PA and PB. So maximizing PA times PB, maximizing PA times PB is same as maximizing the area of triangle APB. So we want to find out when is the triangle APB the maximum, at what position of the point P on the circumference. To find out the maximum value of the area of triangle APB, let's mark the center O and let's draw the diameter through O to the diameter perpendicular to AB through O. Our claim is that this point P, let's call it P1, is that desired position. That's it. That is what our claim is. So P1 is the desired position. Now why is it so? Well, if you take any other point P, let's drop a perpendicular from P on AB. Let's call this point D and this point as D1. So notice that P1D is greater than PD1. P1D is greater than PD1 because diameter is the largest chord. Whatever other chord you draw, that will be smaller than the diameter. Whatever other chord you draw, that will be smaller than the diameter. So clearly P1D is the largest height that is possible. And what is the other way of computing the area of triangle APD? The other way of computing area of triangle APD is half of AB times the height. And the height H is maximum. The height H is maximum when P is at the position P1. When P is at the position P1. That's because the diameter is the largest chord of the circle. So at this position P1, the area of the triangle APB maximizes, and therefore PA times PB also maximizes. So times PB is maximum when P is on the diameter perpendicular to AB, and of course you have to take the longer chord. So if AB itself is not a diameter, longer portion of the chord, so if AB is itself not a diameter, then there will be a longer and a shorter portion. So you have to take that position of P, which is the longer, which makes it the longer one. Okay, the other part was to find out when PA plus PB is maximized. So we will be computing that using the first part. So question: when is PA plus PB maximized? So again, if you have a triangle, I'll just draw the triangle PAB, then we know that AB square is equal to PA square plus PB square minus 2 PA times PB times the cosine of theta. This is the theta. So this was the circle. Again, it doesn't matter where P is because the theta will remain the same even if it is here. So cosine of theta will not change. So let's bring AB square plus twice PA times PB cosine of theta to the other side. This is equal to PA square plus PB square. Now we can add twice PA times PB to both sides. So what do we have? We have AB square plus twice PA times PB times 1 plus cosine of theta is equal to PA plus PB whole square. Now notice that this part has several constant things. For example, AB square is constant. It does not matter where P is. AB is the given chord. Similarly, theta is constant, so this is constant again. So the only thing that will affect the value of this right hand side will be the value of PA times PB. And PA times PB needs to be maxed out, needs to be maxed if this one, that is PA plus PB, we want to maximize this, if we want to maximize this. And we know when PA times PB is maxed out, it is when, precisely when the point P is on the diameter perpendicular to AB. So we already solved it. So the same position of the point P will work. So quite a beautiful problem. You can we have used certain properties of the area of the triangle to find out the maximum position, the optimum position of the point P.